Hi Maria, how are you?
Hey Dan, I'm doing pretty well. I'm waiting here for Stephan though because I have a question about Bio 125.
Oh, are you prefecting the course?
I am.
Oh, that's great. How's it going?
It's going really well. We're doing some DNA replication right now, so it's been really fun.
Cool. It's nice to hear that the class is going well. I'm teaching Bio 126 in the spring, so I look forward to meeting the students that are taking 125 this term.
Yeah, great. They're really great.
Great. So what's Stephan doing?
I don't know. He told me that he had to track some escaped reptile.
For the love of God! Oh, hi, Dan, Maria, how you doing?
Good. What's going on in there?
Dan, I was hoping you could take Brutus back to his pen.
Is it safe?
He's been heavily sedated. I think he'll be just fine.
Okay.
I need to clean up the mess in there, but
okay.
Thank you.
Sure.
All right, take care. Maria, what's going on?
I had a question about DNA replication. I was wondering if I could ask you.
Sure, we'll head down to a room. There's a whiteboard. We'll talk a little bit about DNA replication.
Okay, great.
I'm sorry I had to keep you waiting, but we had to contain Brutus. Back in 2012, we had quite an incident with him, so it was about time we took care of him.
Yeah.
But you had a question about Bio 125?
Yeah, I did. I understand that there's continuous and discontinuous DNA replication.
Of course, yeah.
But does that mean that there's two different polymerases working at the same time?
That's a great question, Maria, and it gives me a chance to review one of my favorite subjects, DNA replication. But let's put your question into the larger context at first. So over here, we have a bidirectional DNA replication fork. So this bubble is going to be expanding to the right, and the bubble is going to be expanding to the left. I have blown up one of these forks. I have blown up this fork right here and represented it as this particular replication fork. The entire direction of DNA replication is going to be in this direction. So you asked, is there one or two DNA polymerases? And in fact, yes, there are two DNA polymerases, one for the discontinuous strand and one for the continuous strand. They often are thought to work together as a complex, but for our model and description here, we can separate these out. But I have a question for you. Which of these two template strands is going to be replicated in the, let's say, continuous direction?
Well, I know that the newly synthesized strand for continuous replication would be replicating in the 5' to 3' direction.
Correct.
So I think it's going to be this top strand.
Exactly. But first, a primer has to be added. The enzyme primase will add an RNA primer. This RNA primer will end with that all-important 3' OH group. And then one of our DNA polymerases can attach. One of our DNA polymerases will attach to this RNA primer and then synthesize in the 5' to 3' direction. So let's just leave our DNA polymerase right here at the replication fork. All right. However, on the discontinuous strand, we're running into the problem of having to go 5' to 3'. And so in this case, we have to do it in a series of Okazaki fragments. So an RNA primer is laid down, and then the second DNA polymerase involved in this will extend in the 5' to 3' direction. Yes, this is going anti-parallel. This polymerase is now free to sort of backtrack. There will be another RNA primer laid down close to the replication fork, and then DNA polymerase will extend that again in the 5' to 3' direction. 5' to 3' direction. And yes, there are two DNA polymerases being involved.
But Stephan, aren't these RNA primers going to be an issue when DNA replication is finished?
Yes, having these pieces of RNA in the final DNA product will be a problem. I mean, not only do we need to remove the RNA, but we need to make this one continuous, covalently continuous piece of DNA. So there are a few more enzymes, as you may have remembered from lecture, that we're going to need here. The first enzyme we're going to need is something to remove the RNA. And so what is that? What was that enzyme?
RNase?
RNase. And so the RNase duty will be to come in and degrade the I'm just going to do this one right now. Same thing will be happening over here. So the RNase has removed the RNA. We now need to fill in this gap right here. What enzyme do we need there?
Well, I know that polymerase is what's making this strand, so DNA polymerase 1.
Exactly, the other DNA polymerase 1. And so DNA polymerase 1 will see this 3' OH group from the last Okazaki fragment. It will attach to that 3' OH and continue its synthesis right up to the end of this Okazaki fragment. Okay? We're almost done. We removed the RNA, we replaced it with DNA, but we still have a sugar phosphate that needs to be connected. We need to create a phosphodiester bond. And what's our third enzyme we're going to need here?
DNA ligase.
You got it. DNA ligase. It will create this phosphodiester bond, making a continuous piece of DNA. So not only is the RNA gone, but we now have a continuous stretch of DNA.
So I understand DNA replication now, but what happens to the end of the discontinuous strand?
Maria, that is a fabulous question, and I wonder how many students in the Bio 125 class caught the problem at the very end of the discontinuous replicating molecule. Now, I'm not going to ask them this on the exam, but if they were curious, let's talk about that a little bit. So, I'm going to erase this top strand here, and let's just deal what's going to happen with the bottom strand. So, a series of Okazaki fragments will happen. As the replication fork opened up, another RNA primer, and then DNA polymerase 1. And at the very, very end, another RNA primer, and then DNA polymerase. All of these going 5' to 3'. Maria, I'm going to let you do the honors of playing the role of RNase and remove all those RNA primers. Okay, we know they're going to be removed. 2, and even the one right at the end has to be removed here. Okay, those are all removed. Now, DNA polymerase 1, going 5' to 3', right there, we'll fill that up. We'll fill this up. Okay, a little bit of a problem right here, right?
Yeah.
Because 5' to 3' is this direction, but there's nothing over here to prime onto.
Right.
So, could DNA polymerase maybe go right to left?
I don't know.
No, it can't. Right? It can't. That would be going 3' to 5'. DNA
Right.
polymerases cannot do that. And in fact, it is I guess it's life. That the ends of our chromosomes, after every round of replication, get a little shorter. Once that RNA primer is removed, we cannot replace it. In all of our somatic cells, our chromosomes are getting shorter and shorter and shorter after every round of replication. It's not the problem in the somatic, that is the problem in the somatic cells. It is not a problem in the germ cells. We have a specialized enzyme that actually fill in this gap. And if they want to know the answer to that, Bio 240, spring term, Carleton College, you got to take the course. All right.
By the way, Stephan, what does the fox do?
Oh, you're going to have to ask some Scandinavian researcher named Jelbus about that one. I think you'll find also on YouTube something about that.
Cool.
Let's go back.
Yeah.